Okay, we're back. We're going to do the back side of this worksheet, part 2 here. We're going to take it up a notch with these trig expressions right here. We're going to make a table here, and I know some people still might be saying, well, why am I bothering to plug in points? I'll just change it to rectangular form, and if it's an ellipse, I'll just draw the ellipse. I'm good. But remember, one thing, that won't show you the direction of the curve. And 2, sometimes you can get some funky little things. So watch out here. We'll have 0. Again, I'm going to go with the quadrantal values to plug in. We'll go 0, pi over 2, pi, 3 pi over 2, and 2 pi. X is 4 cosine of theta. So 4 cosine of 0, that's going to be 4. Pi over 2, that's going to be 0. Pi, that's going to be negative 4. 3 pi over 2, 0. 2 pi, 4. So you're thinking this is easy. I got this. And now watch out, because y's got that sign squared in that. So just be careful with your order of operations. Plug 0 in. Sine of 0 is 0, and 0 squared is still 0, and 0 times that is still 0. So not a whole lot interesting there. Plug pi over 2 in, you get sine of pi over 2 is 1. 1 squared is still 1, and then times 2. Pi, you get 0. Now 3 pi over 2, be careful here. 3 pi over 2, sine of 3 pi over 2 is negative 1. And negative 1 squared is positive 1 before you multiply by that 2. So you actually get positive 2 right back. And 2 pi, you're going to get 0 again. Now watch what this does when you plot these points. 4 comma 0, that's the first point there. Then it went to 0, 2, which is right there. Then it went to negative 4, 0. And then it went back to 0, 2, and then back to 4, 0. So what's happening here? It went like this, and it seems like, unless it goes further, and maybe after this point, if you plugged in something between here and there, maybe it went back and came back here. But I don't think so. If you plugged in, for example, 7 pi over 6, if you wanted to try to do something here, 7 pi over 6 into cosine would give you root 3 over 2, well, negative root 3 over 2, and negative root 3 over 2 times 4 is negative 2 root 3. 7 pi over 6 into sine, that'll give you negative 1/2, but negative 1/2 squared is positive 1/4. 1/4 times 2 is 1/2. So negative 2 root 3, comma 1/2, that's just really going to put you right around in this neighborhood. So you're sitting right on this curve. You're not going anywhere. So actually, I mean, as far as the directions go, it's almost like you could draw double arrows. But now let's see what we get. What is the equation of this thing? And we're going to do it a very similar way, that I'm going to take this and I'm going to isolate cosine. And this, I'm going to isolate the sine squared. I'm going to isolate the trig part of it. And why bother to take the square root and go any further? Because the identity that I'm plugging them into is, cosine squared plus sine squared equals 1, or sine squared plus cosine squared. The order doesn't matter here. So cosine is x over 4. And sine squared, I already have sine squared. It's just y over 2. So you just take out that whole chunk, and x over 4 needs to be squared to give you x squared over 16. But look what that leaves you with. You've got this kind of equation where only x is squared and y is not. You probably should recognize that's a parabola. If you want to isolate y, that'd be fine. To make it look a little more familiar here, if you like, that would be 1 minus x squared over 16, and then multiply both sides by 2. And you're left left with y equals 2 minus x squared over 8, or 1/8 x squared. So what you've got here is a parabola with its vertex at 0, 2. It's opening down because of that negative coefficient in front of the quadratic. But here's the thing. They didn't tell us to limit theta to any particular values. You can plug in anything you want, but you're never going to get off this one little piece. It's not a full parabola. It's only a portion of a parabola. And if I told you to draw this, I hadn't done any of this parametric stuff. If I just told you to draw this, you'd be drawing a full parabola going all the way down. You know, the range would be in negative infinity to 2, and the domain would be all real numbers. So what we have here is sort of a restriction that came about, and we have to account for that. We have to restrict the domain. Yes, we got this equation, but only for certain x values. So sometimes you have to include this additional restriction. And so I got this parabola, but it only exists for x values between -4 and 4. So I'm going to include that additional restriction. You could use inequalities or interval notation. But that's a weird thing, and sometimes that's hard for kids to comprehend, that you've got to remember to add your own restrictions if what you're graphing is not the full graph of what this equation is. All right, now we'll try one more here. This is not a trig example. I know, you love trig, but you love this just as much. E. Got that natural base there, named for Euler, the Swiss mathematician. So let's see. X equals e to the 2t and y equals e to the -4t. Make a table. Okay, doesn't tell us any particular restrictions on t. So I'm going to try a couple negatives and a couple positives. Unless there's any sort of domain restrictions here, but t is this exponent. You can plug in anything you want for exponents, negatives, zeros, positives. So why not try a little bit of each just to get a sample of what's going on. If you plug -2 in here, you'll get e to the -4, or 1 over e to the 4th. When you plug in -1, you'll get e to the -2, or 1 over e squared. When you plug in 0, you'll get e to the 0, and we know e to the 0 is 1. Plug in 1, you'll get e squared, and so that's 2.7 squared. It's 7 point something or other. E to the 2 times 2, that'll be e to the 4th, so 2.7 to the 4th power. You know, it's kind of a big number. We'll just leave it there for now. The y values, you're going to get very similar, but when you plug in a negative, that already has a negative coefficient there, so you're going to get e to the +8th. When you plug in -1, you get e to the 4th. Plug in 0, you'll get e to the 0, which is 1. Plug in 1, you'll get e to the -4th, or 1 over e to the 4th. Plug in 2, you'll get 1 over e to the 8th. Okay, so I think you have an idea at least of what's happening. As you plug in bigger and bigger t values in this direction, the x value is just going to get huge, while the y value is going to get very, very small, but it's never going to get to 0. You're just going to keep getting 1 over e to the blah, blah, blah. If you plug in 3, 1 over e to the 12th, 1 over e to the 16th, etc. It's never going to get to 0. And in this direction, it's the exact opposite. Y is getting infinitely large, and x is getting infinitely close to 0, but never going to get there and never going to be negative. So sketching this graph, definitely a little weird to be thinking of sketching these values. If you need your calculator, you could, I suppose, check it out, but you should be able to estimate here. 1, 1, that's definitely a point that's easy to plot. It's a rough sketch. I don't even have a graph here, so 1, 1, 2, 2, 3, 3. e squared 1 over e to the fourth. Well, that's like 7 point something, and this is getting very close to 0. So I'm just going to put a dot down here. We're getting close to 0 as we move to the right here. And that's going to keep getting closer to 0 as I go further to the right. As I go to the left, x is 1 over e squared, which is a very small value, close to 0, and y is getting very big. As I get closer to 0, y gets very big. So I'm really looking at something like this. But in which direction was I moving? As t increases, we got this point, which is up here, and then as t increases, now we have this, and then 1, 1, so we're moving in this direction. But notice, we've got a vertical asymptote here because we're never going to get to 0 for x, and we've got a horizontal asymptote. We're never going to get 0 for y. So let's check it out. Let's change this to rectangular form. You got a couple ways to do this. You know, like I've said before, I'll maybe show you the slightly longer way first, because that's what math teachers like to do, and then I'll show you one that's maybe a little quicker. You know, it's good to know both in case one isn't working out for you. If you have x equals e to the 2t and y equals e to the negative 4t, I'm going to isolate t in one of these. So let's solve for t on either one of these equations. I may as well do it on this one. If I solve for t here, I got to get it out of there. That means I'm going to take the natural log of each side. So ln of x equals the ln of e to the 2t. And of course that's going to leave me with ln of x equals ln of e to the anything is that thing. We get ln of x equals 2t, so t is equal to 1/2 ln of x. Now I'm going to take that and substitute in for t into the other equation. So we're going to have y equals e to the negative 4, and in place of t, I'm going to put 1/2 ln of x. Negative 4 times 1/2 is negative 2 ln of x. And I suppose this would be fine, but you might say, I could play around with this a little more using some log properties. This coefficient can be made an exponent of your argument here, so that could be that. And now e to the ln, again, those are inverse operations, they cancel each other out, leaving you with just this, which with a positive exponent is 1 over x squared. And that should make sense because this graph has a vertical asymptote at x equals 0 because it makes the denominator 0, and that's undefined. And it also has a horizontal asymptote of y equals 0 because the degree of the denominator is larger than the numerator. So we've got this. However, we have to restrict the domain again because if I were to graph this, it would consist of not only this, but it would have this other piece over here. It kind of looked like a volcano, if you remember those graphs. And we don't get that piece from this. So I have this equation, but only for x values that are greater than 0. Okay. Oh, I did say there was maybe a slightly faster way to do this particular problem if you want to avoid using logs. If you're kind of clever with your algebra, here it is, x equals e to the 2t, and probably some of you would have figured this out anyway. Some of you might like it better. You see x and y are very similar. They're both defined as e to a particular power, but they're not quite the same power. So one thing you could do is say, maybe I could make these two things be the same. So, for example, if I were to raise this side to the negative 2, that would make negative 4t, because power to a power, you would multiply that. So I'll just raise this side to the negative 2, and now what I'll have is x to the negative 2 is equal to e to the negative 4t. And now, if they each equal e to the negative 4t, well then they must equal each other. So I can just say y equals x to the negative 2, which leads us right to here, but again, still with that domain restriction. All right, very cool. Hit me up with any questions you have, and stick with it. These parametrics can be a little tricky at first, but they're not too bad. So good luck, everybody. I'll be talking to you soon.